partly because it's linked to assignment 4, maybe I'll show you a feature of AnyLogic that has some relevance for this. So the question has to do with how can we support special functions or relations, functional relations between A and B, for example, that might not fit in neatly to simple arithmetic expressions, something like that. Well, one construct that AnyLogic does provide, and this is based on a history of system dynamics support for this, is something called a table function. Okay, and this is basically allows you to define arbitrarily and graphically, if required, a lookup function that specifies, you said evaporation as a function of temperature, evaporation for temperature, something like that, right? And this might be a function. I do ask you to define this for the final assignment. So this might be a function that will depend on temperature. And here, what we're going to do is we're going to have the, so I'm going to name this better. Naming is important. Evaporation rate for temperature, okay? And what we're going to do is, and this is going to be profoundly crude. I don't profess to be able to put in an actual detailed equation here. But maybe I say temperature 0, there's 0 evaporation because there's ice or something like that. Maybe there's some sublimation or something. Okay, so fine. Maybe I'll do 0.1% evaporation or something. Maybe at 10 degrees, it is you know a 0.5%. Maybe at 20 degrees, now we're up to, I don't know, 1% or 1% per day is still a lot of a reservoir. 30 days or 30 degrees, maybe it's 0.02 or something. I don't. Again, these are fictional values that I'm just making up here. But you'll notice you can define over here. You can actually drag things here, and hey, I thought you could. Hey, oh man. Well, it was a nice idea. Beautiful theory. I thought. Okay, maybe I'm missing something, but I thought you could actually drag them graphically to sort of, it would correct it. But you'll notice that we can specify how to interpolate between these points, to do so linearly or do so as a step function, so it jumps up at these points, or to do so with a spline where it tries to capture with a nice curve that and then you can I think there's an approximation. You have a straight line, a linear approximation to them. So maybe for now I'll do a linear, just piecewise linear, and maybe we'll have temperature vary by season, right? Okay, so I won't try to provide the complete temperature of Saskatoon here, but maybe we'll have a auxiliary variable here that's temperature for current time. Yes, Farhad. Okay, so the table itself is a function that is a mapping from on the one hand this domain on the x-axis to a range here. I believe it's static, but I can't say for sure. By the way, I'm asking how it's handling out of range values. So the question is, can it be manipulated dynamically? Could you change it? I'm not sure, but what I will tell you this, as far as linked to distributions, you can create a distribution that's distributed according to this function by creating what's called a custom distribution here. And maybe I'll show that in a bit, okay, afterwards. We'll get to that. It's a great question. Okay, so let's do evaporation rate for temperature. First, we define temperature for current time. Maybe I'll have this defined according to a sine function. So in the span of 365 degrees, in the span of 365 days, we'll go a full range up in spring, down in, with max at summer, down in fall, and then a low in winter, and then back up, something like that. Okay. The only problem is that January won't be the coldest month. It'll be at 0 there. So anyway, okay. So I'm going to do a sine. I'm going to do 2 times. Is there a math.pi? I hope there is. Oh, yes. Okay. Divided by 365.2524, I think it is. And then I'm going to have time in here, the current time, and but I'm gonna shift it by a certain amount. Yeah, you and I were thinking the same way. So how much should we shift it by? Sorry? Yeah, minus pi over 2. Is that right? Pi over 4 by 45 degrees. Okay. Yeah. Okay. So math dot pi over math dot pi over 4, something like that. You're saying, or are you saying over 2? Because pi over 2 would be 90 degrees, right? It would shift it out. Yeah. Yeah. I think that would be better. So is it plus or minus? We want it to start when it's negative, to start really cold, right? So this, I think this will be okay. Okay, ladies and gentlemen, we're gonna run this right now just to see what happens, and see if that looks okay, and then we'll piece together the other components. Okay, so here we go. Where's our temperature for current time? Let's create a graph of this. Okay, here's a graph. Oh, it's going forward day by day by day. Let's speed it up. Okay. Okay, it's warming up from January by each successive month, and here about 3 months in, oh, it's maxing out 3 months in. That's a little bit it's a little bit premature there, but I don't want to get caught up in this. It also stops at 100 days, which I'll have to change, but I'm going to leave it like that for now. Okay, so okay, that's great. So there's the oh, we got to multiply this by something. So what does it go between 30 degrees times this? So it's at a minimum minus 30 and a maximum of plus 30. What do you say? I say yes. Okay. So let's now connect this up to this evaporation rate for current time. Okay. Hey, I don't think we can connect this guy up. I don't think the semantics are such that you can do that. It doesn't connect. We'll just have to refer to it. Okay. Boom. Kill it. Okay. So temperature for current time, we want to right. So we want to use temperature for current time. Okay, that's the current temperature, and then we want to apply the evaporation rate for the temperature as if it's a function, right? Evaporation rate for current time, and I actually forget the with this. What do you do? Do you just call it? Do you just call it on this thing, this table function? I actually can't remember, so let's see. It's probably going to give us an error. No, it's a happy camper, so we just call it on it. Okay. So, sorry. So that would be most odd if it were a happy camper, but okay. Now it's unhappy. Yeah. So it doesn't like that. Oh well. I don't know what was going on there, but I thought it thought it was a happy camper. Okay, so we have to call something on this thing, and I'm trying to remember what it is. How do you look up a value in this thing? So this evaporation rate for current I did it the wrong one. Oh man, evaporation rate for temperature. I did the wrong one. See, yeah, you just provide it to it as a function, and you provided temperature for current time, right? Okay, let's see if it's a happy camper now. It is. Okay, and let's run it now. And let's go see the evaporation rate change over time. Okay, so here we have this function. The function is static. This temperature is varying day by day by day. This evaporation rate is also varying day by day by day according to this mapping here. So this function translated temperature into evaporation rate, and that evaporation rate is then applied to this evaporation rate for current time to set that, which is used to update this flow rate here, right? So we can run this thing, and it only runs out to 100 days, but you could see there's kind of kinks in this. It's no longer a sinusoid. By contrast, this here is sinusoidal, but this one is this kink associated with temperature changing, impact of temperature on evaporation. Okay, so that was an arbitrary function that was just asked about. So I'm going to stop this, but now I'm going to